In this video, we're going to look at the idea of graphing spheres. So for our example, we're going to graph the surface x squared plus y squared plus z squared equal 9. We're going to do that using contour curves. So the idea here is to plug in some various z values and to figure out what the horizontal cross sections of our surface are going to look like. So let's try plugging in z equals 0 here. Plug that into the equation for our surface and we get x squared plus y squared equal 9. So in other words, that's giving us a circle of radius 3 in the xy direction when z is equal to 0. If we were to use, say, z equal 2, our equation would look like x squared plus y squared plus 4 equal 9. So that might look a little bit nicer if we just rewrite that more cleanly. So let's just rewrite that as x squared plus y squared equals 5, and that's giving us a circle of radius root 5 in the xy direction when z equals 2. Okay, let's try one more positive z value, like z equal 3, for example. Our equation would look like x squared plus y squared plus 9 equals 9. Or if we write that more concisely, x squared plus y squared equals 0. So in other words, that's giving us a circle of radius 0, or if we think of that differently, that's just saying the x and y values are both forced to be 0. So at z equal 3, x and y are both equal to 0. Okay, let's try a negative z value. Let's go z equal -2, for example. Then we'd have x squared plus y squared plus 4 equals 9. In other words, that takes us back to this situation that we saw above. When z equal 2, we already said that we're producing a circle of radius root 5, and that same thing is going to happen when z equal -2. So circle of radius root 5, and that's telling us that we've got symmetry in the z direction. Now, you could try something like taking a z value that's quite large in absolute value, whether it's positive or negative. We could try something like z equal 4. We'd get something like x squared plus y squared plus 16 equals 9. Or if you simplified that, you'd have x squared plus y squared equals -7. There's no solution, no real solution. So there are not going to be any points on our surface if z gets too big in absolute value, whether it's large and positive or large and negative. Okay, so let's see if we can put this all together into a graph. So we'll draw our 3 axes. Here's our x, y, and z directions. And we're certainly going to want to go at least 3 units in each of these directions. Okay, and let's see if we can draw our contour curves. So at z equals 0, that's when we're sitting in the xy plane, we're getting a circle of radius 3, so that might look something like that. At z equal 2, we're getting a slightly smaller circle, a circle of radius root 5. I'm not going to draw that just to keep the picture clean. And by the time we get up here to z equal 3, the only point that we're getting in the xy direction is just that point where x and y are equal to 0. Okay, and then if we move down in the negative z direction, same kind of thing is going to happen. By the time we get down to z equal -3, we're just going to have that single point where x and y are equal to 0. If we go beyond z equal ±3, then we're not getting any points on our surface. So what we're producing here is actually a sphere. I'm going to draw the entire thing so that we can see it. So that's not the best looking sphere. Normally when I draw a sphere, I just try to draw a circle and then put a bit of a loop on it to give some perspective. So you could say this is a sphere of radius 3. So we know it's radius 3 just from looking at the xy plane. That's the widest point of the sphere when we're looking at it through horizontal cross sections. So it's a sphere of radius 3, and if we wanted to be more specific, we could say it's centered at 0, 0, 0. In other words, centered at the origin. So now that we've seen a first example of graphing a sphere, let's talk about a couple of transformations. So if we see the equation x squared plus y squared plus z squared equals r squared, we should now recognize that as a sphere of radius r. So we're just using capital R here for the radius, and that's centered at 0, 0, 0. So centered at the origin. If we like, we could shift that sphere. We could do something like x minus 1 squared plus y plus 2 squared plus, let's say, z plus 3 squared equals r squared. So that now is still a sphere of radius r. But if we think about where that's going to be centered, so that is actually centered at the point 1, -2, -3. So x minus 1 shifts you to x value positive 1. If you see something like y plus 2, you're now shifting your origin to y coordinate -2. And if you see something like z plus 3, that's shifting the z coordinate of the origin to -3. So let's look at one final transformation just in the form of an example. Let's try to graph the surface x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. So in this type of equation, you would typically see a 1 on the right side. There would never be a need to have 2 or 4 or any other number on the right side because we've chosen to divide through by whatever creates the 1 on the right side. So if we wanted to graph this, my trick for getting some points on the surface would be to let both x and y equal 0. Let's plug that in and see what that means for z. So if x and y were both 0 in this equation, we would end up with z squared over c squared equals 1. In other words, that tells us that z squared equals c squared, and that gives us two different possible z values. So z could be either plus or minus c. And you could do this for any pair of variables. So you could say let x and z be equal to 0. You could say let y and z be equal to 0. And in each case, what you would be figuring out is the possible values for the third variable. So if you did this with x and z equaling 0, you would find something like y equals plus or minus b. And if you did it with y and z equaling 0, you would find that x equals plus or minus a. All right, so in other words, when we let x and y both equal 0, we were producing 2 points on our surface. One was 0, 0, c, and the other one was 0, 0, minus c. So let's see how knowing those 2 points would help us graph our surface. Okay, let's draw our axes here. So here are x, y, and z axes. And let's just talk about that first point, 0, 0, c, for a second. So that's one of our z-intercepts. Let's say that point is up here. So that's our z value c. And there's a second z-intercept over in the negative direction of z. I won't draw that for now, just because I want to keep the picture clean. Okay, and then in the y direction, we're getting a y-intercept of plus or minus b. So let's say this is b right here. Let's say this is b units along the y-axis. And let's say over here, say this one is a units along the x-axis. Okay, so let's see how to draw this surface. Well, basically, these 3 points here are going to give us some of the vertices of the surface that we're going to be graphing. So let's think first about what's happening in the xy plane. So we're actually getting an ellipse in the xy plane, where these 2 points are 2 of the vertices on that ellipse. So I'm just going to draw with some symmetry. We know we're going back through the point 0, 0, negative a, 0, 0 as well. So we're going backwards to an x-intercept of negative a, and we know that we're going through a y-intercept of negative b as well. So just trying to draw some symmetry in that xy plane, and we're creating that ellipse passing through these 2 points here. So let's draw similar things for what's happening in the xz plane and the yz plane, and that will give us a pretty good picture of what our surface looks like. So in the yz plane, I'm going to switch to a different color now. Let's do this in red. So in the yz plane, we're passing through this point here, this point there, and we want to bring some symmetry into this picture, so we know we're passing through a y-intercept of -b and a z-intercept of -c as well. So we'll just draw what looks like an ellipse in the yz plane passing through those 2 points. Okay, and then the slickest way to complete our picture here is just to draw a third ellipse that's passing through the vertices that we've already illustrated. So I'm just going to do that in blue. Let's create a third ellipse here that's just going through all those vertices that or the outermost vertices that we've already drawn. So passing through the outermost of the 2 vertices of both of those ellipses. Okay, so this surface that we're creating, this is called an ellipsoid. So an ellipsoid is just the version of the surface in 3-dimensional space that gives us cross sections that are ellipses. So we could say this is an ellipsoid. It's centered at the origin. And the quickest way to make that sketch is just to figure out what the x, y, and z intercepts look like. So let's do a quick recap here of graphing spheres. We've seen that the equation x squared plus y squared plus z squared equals r squared gives us a sphere of radius r centered at the origin. We can shift in the x, y, and z direction. If you see something subtracted from the x value, that means that the x coordinate of our center is actually going to be at a positive number. So if you see x minus 1 in the equation, that center is getting shifted to x equal plus 1, for example. And then third transformation we talked about this idea of the ellipsoid. So that's where we've got our x squared, y squared, and z squared divided by some squared quantities. So in other words, divided by some positive numbers. And we'll always have a 1 on the right side in that situation. That is creating an ellipsoid that's centered at the origin. Thanks for watching.